Welcome. In this session, we'll talk about the representation of a complex number on a complex plane. In the last session, we learned how to represent the complex number. We learned there are several representations that we can use complex. For example, we can write a complex number as A plus iota B. In electrical engineering, we say A plus JB. I is reserved for current here. So this is called the rectangular representation. A rectangular form of a complex number. Similarly, we can represent this complex number as r at an angle of theta, and this is referred as the polar form of complex number. Okay, now how do we plot these complex numbers on a complex plane? So if we have to draw, for example, if we have to draw this complex number on a complex number, how we let's draw a complex plane first. This is real axis of complex plane, and this is imaginary axis plane. So this is just like a two-dimensional plane, real axis and imaginary axis. Imaginary axis is also referred as j omega and j axis. Okay, let's start with the rectangle form. So suppose we have a complex number. So we can represent this on this plane. Now, depending upon the values of a and b, this complex number will lie anywhere on this complex plane because a and b can be negative or positive. For example, if a is negative, a is positive, and b is also positive, then complex number will lie in this part of this complex plane. It will lie on this side of this complex plane. So this is referred as the first quadrant of this complex plane. So then complex number z will lie in the first quadrant of this complex plane. For example, if we say z is equal to 1 plus j, here a is equal to 1, b is equal to 1. So this complex number will lie somewhere here in this complex plane. Similarly, if a is negative, that means on this side because negative real axis is here. So if a is negative and b is positive, so positive real imaginary axis means this. So then this complex number will lie somewhere here on this complex plane. So complex number will lie here, and this is referred as second quadrant of this complex plane. For example, if we say z complex number is simply -1 plus g. Very simple example. A is 1, a is -1, b is +1. Okay, so complex number will lie in the second quadrant. Similarly, if a is negative and b is also negative, okay, both real and imaginary parts of this complex number are negative, then this is the negative real axis, this is negative imaginary axis. So that means somewhere in this plane, okay, on this side of this plane. For example, if I say z is, suppose z is -1 minus j. So a is -1, b is -1. So this part of the complex plane is called the third quadrant of this complex plane. Similarly, if a is positive and b is negative, now positive real axis means this side. So this is the positive real axis, and negative imaginary axis is this. So it will obviously lie in this side on this complex plane somewhere here. Okay. For example, if we say z is 1 minus j, here a is 1 b is -1. So this part of the complex plane is referred as the fourth quadrant of this complex plane. So a complex number can lie anywhere on this complex plane depending upon the values of a and b. Okay, so we can draw this complex one. As for example, if I say z is 1 plus j, for example, this much is 1 and this is 1 on imaginary axis, then this is our complex number. So complex number is somewhere here, located here. So this is z 1 plus j. Okay, this is the complex number. Okay, all right. So we can draw any complex number on this complex plane using the values of a and b. We can also use the polar form. So if we draw the polar form, if we use the polar form, so the polar form of this complex plane number is r at an angle of theta, where r is called the magnitude, and this is related to r is related to the rectangle components as a square plus b square, under root of a square plus b square, and theta, that's very, very important, is called the phase of this complex number. What do I mean? The phase of this this quantity. And what is this quantity? It's simply a line on a complex plane that is referred as a phasor. In the last lesson, lecture we talked about this. A complex number is also called a phasor. What's a phasor? It's simply a vector in two-dimensional plane. It looks like a vector. Well, just like we used to do vectors in two-dimensional plane, a phasor is a vector in complex plane. How is this phase related to this? The rectangular components phase is given as tan inverse imaginary part divided by real part. Okay, now if we use this representation to draw this complex number on a complex plane, how we do that? So we draw the imaginary, real and imaginary axis of this complex plane. This is the real axis. This is the imaginary axis. So this is imaginary axis. This is real axis of this complex plane. So based on r and theta, how we draw this? Now, depending upon the value of theta, we move on this complex plane accordingly. For example, if we theta is measured from this real axis, so how do we measure first of all theta? Theta is measured from this real axis. Depending upon whether the theta is positive or negative, we move accordingly on this plane. How we do that? If theta is positive, we move from this real axis in anti-clockwise or counterclockwise direction. So this is called the anti-clockwise direction. So we move in this direction if theta is positive. So if theta is positive. Similarly, we move in this direction if, and this is referred as clockwise direction, if theta is negative. So in order to draw our theta, how do we select the direction, or how do we move on this complex plane? Because we have to draw a vector, and this is a phasor representation, and simply a phasor is a vector. So to draw this vector, how do we move on this complex plane? First of all, we check whether theta is positive or negative. So when we have decided, when we know theta is positive, accordingly we move on this plane in the clockwise direction or anti-clockwise direction. For example, if we say the complex number in is 1 plus j, and we can write it in the polar form as under root of 1 square plus 1 square, that is under root of 2 at an angle of tan inverse 1 by 1, that is 45 degrees. So if we have to represent this, since theta is positive, so we'll write it like this: a vector that has a magnitude of under root 2 and makes an angle of 45 degrees with a real axis. That's how we draw this on a complex plane. So this is our z. Okay, this is our z on this complex plane. All right. So this is how we draw. Similarly, if the theta is negative, we'll move in the clockwise direction. Okay. Now here is one interesting point about drawing the while we draw this phasor or a complex number in the polar form on the complex plane. See, while we convert the when we convert this a plus jb to this polar form, that is r at an angle of theta, where r is under root of a square plus b square, and theta is phase or the angle that this phasor makes with the real axis, tan inverse b by a. And we calculate this from using the applications like the calculator on mobile phone, or the scientific calculators like Casio FX1991 FX991 ES, if I remember the name correctly, or FX991 MS. When we use these calculators, when we substitute the value of A and B, say the calculator or the mobile application, calculator application on mobile phone will always return this theta in the range from minus 90 to plus 90. Minus 90 degree to plus 90 degree. Okay. So when we use these application or these scientific calculators, the theta will always be in the range. So where is the minus 90 from to plus 90? So we measure the angle from this axis. So 90 degrees, minus 90 degrees from this to this. So this is, the result is saying that this phasor or the complex number will lie in this quadrant or in this quadrant here. This is 0 to 90 degree. In other words, the result is saying me that the vector in the complex number is lying in the first quadrant or fourth quadrant. What is first quadrant and fourth quadrant? This is the first quadrant and fourth quadrant. So the result tells us that the complex number always lies either in first quadrant or fourth quadrant. For example, one problem, let me illustrate this what I meant by this. So suppose z is minus 1 plus j. How much is a? A is minus 1, b is plus 1. So if we try to calculate r will be simply equal to under root of minus 1 square plus 1 square, that's equal to under root of 2. Similarly, what will be theta? Tan inverse 1 divided by minus 1, that's equal to tan inverse minus 1. Tan inverse minus 1 is simply minus 45 degrees. So if we try to solve this on these applications like Casio calculator or the calculator application that is given on your mobile. So this simply says that the phasor is lying in the fourth quadrant, where here. So if we draw the complex plane, the result says that we should draw this phasor like something like this. So this is real axis, this is imaginary axis. So the vector has how much length or magnitude under root of 2, and that angle it makes 45 degrees. So we'll draw a vector that has an angle minus 45 degrees. How do we measure minus 45? This is the minus 45. Okay, we move in the clockwise direction, and the length of this vector is, and that's what the result says, but which is clearly incorrect. This vector or this complex number is lying in the fourth quadrant. How? Because a is minus 1, b is plus 1. So this should lie somewhere here in this plane. So the result that it returned is incorrect. Okay, so how do we solve this problem, or how do we correct this result? What we do, so whenever you try to plot a complex number on a complex plane, first of all, check the real and imaginary part. So the first thing that always you will do is you will check its real part and imaginary part. Now real part here is minus 1, imaginary part is minus 1 lies somewhere here and plus 1 lies somewhere here. So this tells us that the complex number lies in the second quadrant of this plane. So if we redraw this complex plane and draw it like this, so this is real axis and this is imaginary axis. Now if we use the in this rectangle form, this is -1, this is +1. So somewhere here, the complex number lies here, somewhere here on this complex plane. Okay. Now, if I have to use the polar form, so how do I do this? But if we use the calculator, the result says this has a length of 2, but angle is -45. So how do we rectify this angle? Simply, whenever the result comes, whenever you know that the complex number lies in second or third quadrant, simply add 180 degrees with this. So if you know that the this complex number lies in second and third quadrant, simply add 180 degrees, whatever is the value given by the calculator. For example, in the above case, the value returned by the calculator is -445. So the actual angle of this that it makes with the real axis will be -45 plus 100, -45 plus 180. That is, I think, 135 degrees. So the angle that this makes with the real axis will be actually 135 degrees, and it is plus, so that means we'll move like this on this complex plane, which is correct. You can check this is correct, and this is 90 plus 45 is 130. So this is the correct representation and magnitude of this. Okay, so let me explain it this one more time. Suppose we are plotting a complex number on a complex plane. The first thing you need to check is always whether the complex number lies in first, second, third, or fourth quadrant. Okay, that's the first thing you'll have. Otherwise, if you will do it using directly the calculators, commonly used calculators, or the calci application on the mobile phone, the result may be wrong. Why? For example, here is one example. If we do this using an ordinary calculator or the scientific calculators, the result return is that the vector had that the phasor has a magnitude 2 and angle is -45. So this says that we should plot it like this, which is incorrect or which is wrong, right? This is clearly wrong. So how do we correct or rectify this problem? What we do, whatever is the angle returned by this calculator, we add 180 degrees to this and we plot it like this. Okay, so this is the correct plot of this complex number. This is the correct plot of this complex number. Similarly, let's study one more example. For example, let me take a very simple example. Z is -1 minus J. So how much is A here? A is clearly -1, B is -1. So what will be the magnitude of this phasor or complex number? This will be -1 whole square, -1 whole square, -1. So that is +1, that is under root of 2. So magnitude is +2. Now, theta is tan inverse minus B by A. B is -1, A is -1. So that is tan inverse 1 by 1. That is 1. Tan inverse 1 is simply 45 degrees. Tan is 1 and tan is equal to 1 at 45 degrees. So this, if I use this data and try to plot this complex number on a complex plane, so what will be the result? So result is something like this. If I try to plot this using this data, so this is real axis, this is imaginary axis. So I will draw a vector that makes an angle of 45 degrees with this, and the magnitude of this is under root. So this is what the result is, but this is clearly wrong. Why is this wrong? Why is this wrong? Can you tell me why is this wrong? Because the vector clearly lies in the third quadrant, because here both real and imaginary parts are negative. The vector clearly lies somewhere here. So how do we rectify this angle? So the actual angle that we'll calculate from this will be simply, to rectify this, we'll say theta actual in this case will be simply theta plus 40, this 180 degrees. How much is theta returned by the calculator? 45 degrees plus 180 degrees. That is equal to 2 25, I guess. Yes, 225 degrees. Okay, so now this is plus positive 225 degrees. So we'll draw a vector on this complex plane. We'll draw a vector that makes an angle of how much? 225. This is 180. 180 plus 45 is 225. So somewhere here. So this will be the vector. Okay, this is that vector magnitude is this, and this is 225 degrees. So this is the correct way to draw this. Okay, so this result is correct. This one is correct. Okay, so whenever you try to solve the problem of plotting a complex number on a complex line, first thing that you will check is whether the complex number lies in the first quadrant or fourth quadrant. Okay, that's the first thing you will always check. Otherwise, the results that will return by the commonly used calculators like Casio or the mobile, some of the Casio calculators like these are on the mobile phone application may not be correct. Uh, okay, so how do we rectify the problem? Simply, we add 180 degree. If the phase lies in this, if the complex number lies in third second quadrant, we add 180 degree to the angle returned by this calculator, by these calculators, and we get the correct result. The latest calculators, like I think latest calculators, like if I remember it correctly, I don't remember the name exactly. G second, I think doesn't have this problem. If you enter the complex number with the components with the value of A and B, this will give you the correct value of the complex. I don't remember exactly. This is again from Casio. So this is a Casio calculator. Name of this Casio, this will give you the correct value of this. Okay. However, if you use the mobile phone application calculator or the scientific calculators like 991 ES and 991 MS, the result may not be correct. So how do we rectify this problem? We add simply 180 degree to the angle if the complex number lies in second or third quadrant. Okay, I hope you have solved this. I hope you understood. Let me write some assignments here so that you solve these examples yourself and understand this concept better. For example, if we say z is -1 plus 3j, second example is z is -2 minus 2j, third example is 2 minus 5j. Plot these complex numbers on a complex plane, but using phasor representation or polar representation of a complex number. Okay, using this representation, try to plot these complex numbers using this representation. All right. Okay, let me end this session here.